Okay, in the third part of the video related to Euler-Bernoulli beam theory, we would like to make some conclusion that we use in practice related to the uh, only surviving stress element based on the assumption that we have our Poisson effects are negligible, um, and that is moment curvature relation. I have written down here on the side so we can maybe move faster. From analytical geometry, you can actually prove that the curvature for a given curve, which is the inverse of the radius of curvature, is given by this formula. Now, if we assume, which we have in Euler beam theory, we have the slope is very small, therefore the square of slope is very small compared to 1, so we can drop this term and the denominator is 1. Therefore we approximate the curvature for a small slope with d2w dx, or the rate of change of the slope. Now if I come back here and use my results from the stress, I can write the stress as sigma x is minus Ez kappa, which is d2w dx. So this is, if you like, this is stress curvature relationship. Now, I want to relate this to a more practical quantity that we have in beams, and that is um, moments at the cross section due to applied loads. And if I consider a simple cross section here, as sketch shows here, as a rectangular, doesn't matter any cross section the results apply, but for sake of demonstration I used a simple rectangular section. So in this section we have the x, which is the direction that stress applies, and my z-axis here. And then I will consider a differential element here, dA, which is the width of my cross-section B, say, times dz, which is the differential height. Now, the moment for this differential, let's call it dm here, the moment is the force, which is sigma x, times this area, which is dA b dz. This is my force, or differential force, shall we say, dF, acting on this differential element here. And then multiply this by the R, which is Z from the neutral axis. So this is my differential moment. Now I want the moment, then I come here and integrate this along the Z over the area. Shall we say, maybe I call this over the Z. And then my sigma x is minus Ez d2w dx squared. This is my sigma x, b z dz. Now notice that E is a constant, minus obviously, E is a constant, B is a constant, assume here in our example here. So E and B comes out. d2w dx squared is not a function of z, not a function of z. As we know, for any given cross section, that is only a given value. Therefore, the only thing that survives is z squared, because I have one z here, z squared dz. Now, You can keep it actually as dA. I can write these things also as sigma x dA times z. So basically this can be equivalent to integral over a e or minus e d2w dx square z square dA. Doesn't matter. But we are more specific in terms of our example here. Let's move on with this integral. So this integral is z to power 3 over 3. But what is the limits of the integral? From minus h over 2 to plus h over 2, because I consider this is the neutral axis and the whole thing is h. So if you work on this integral for these limits, you get, as I've shown here, these things, and this becomes, actually, is this the moment, we call it moment of inertia of the cross section. In this case, about y-axis, the axis of rotation, axis that bending is applied here. Well, this is my neutral axis, and the y is perpendicular. Y is in this direction. Actually, I can show here y is this direction axis. Okay, so here what I have shown here, this is very typical strength of material calculation. Just I wanted to do it here for completeness of the video. Therefore, I get M is equal to I, call it generalize I, minus E d2w dx square. Therefore, we can write it as M over EI is minus d2w dx square. This is called curvature moment or moment curvature relation. Note here that this curvature, as we discussed before, if I go fast, sorry for that, we discussed it here, that for a positive moment, you get a negative curvature, and for negative moment, you get a positive curvature. And that is exactly why we get a negative sign here, based on our coordinate system. If you reverse the z or consider z upward, then this negative will disappear. So this is consistency for our coordinate system. So if you see some textbooks, they don't have negative, or some do, look at their coordinate system. And you see that if your moment is positive, therefore your curvature is negative, therefore this equality is valid, and vice versa. So here we have to be very appreciative of this relationship that we got in terms of its application. We are saying that if you have an applied load for a given section with some material property and some geometry, the relationship between the moment and this modulus of elasticity and the moment of inertia, as we see here, uh, is actually the curvature with a negative sign. And that is a very profound insight into the mechanics of a beam, in this case Euler-Bernoulli. beam that we are going through, and therefore we can actually calculate for a given bending moment, we can calculate the uh, curvature, and then if you integrate the curvature, you have the slope dw dx, and if you integrate the slope, you have actually the w, the deflection. So for a given beam, material property, as I mentioned, and some geometrical dimension and applied load, we can relate these two together. So basically, if you like, the left side is external, shall we say, and the right side is internal reaction. So if you increase the moment, obviously the curvature will go up. If you increase the EI is rigidity or of the beam, but if you increase the modulus of elasticity, stronger material, shall we say, stiffer material, I should say, then the curvature decrease for a given M. And if you make it a bigger I or a bigger section, then of course also that also decreases the curvature. So that is moment curvature relationship. Okay, in addition to the moment curvature relation, Euler-Bernoulli beam theory is not complete if we uh, doesn't resolve or we don't talk about the shear stress dilemma, or if you like, shear strain dilemma. As you saw before, that according to our kinetics map, uh, we don't have shear stress as a result of disappearing shear strength. So we know that in beam and in beam equilibrium, we we have that we have the shear stress because a beam develops shear force at the section due to the applied load, and it is required to have a shear stress at that section uh, for equilibrium. So we can say that since shear stress is basically the result of the kinetics map is zero, we have to employ the equilibrium to recover it. In another words, we can say that Euler beam theory, based on the assumptions that it makes, the two major assumptions that we discussed, decouples the stress due to bending and the stress due to shear. These two are calculated separately. They don't connect to each other. Uh, so bending stress is a direct consequence of uh, kinematics and of course kinetics of the beam, and shear stress has to recover based on the equilibrium. In a normal theory, well, when I say normal, I don't want to disrespect Euler beam theory, but because of the assumption, it simplifies a lot and it loses this connection. But in general, 3D theory of elasticity or any further theories that we will discuss, like Timoshenko or others like Reddy and other things that we will discuss later, we will see that this connection is not lost. But in Euler beam theory, this connection is lost. And we have to recover the shear stress uh, as a required uh, quantity to satisfy the equilibrium. So as a conclusion, I can say that the shear stress exists physically, but ignored kinematically. Let me write it here. Shear stress exist physically but ignored kinematically in Euler-Bernoulli beam theory. Okay, so how do we recover this? So, okay, we go to the equilibrium. I will not go through the full derivation, but I explain how it can be done. So if again you consider the beam, if you consider the beam, then if I come and consider a slice of this beam, I know that I have to, for example, for a given load, I will develop a shear force on this cross section. So this is, let's call it the shear force V, capital V. And this shear force obviously will create a shear stress at the level that we are considering this element. And if I show just a free body diagram of this element here, let's say I have a stress here, so I should have an equivalent stress on the top and obviously at the bottom, right? We see that these stresses that are developed on plane perpendicular to the, so this is my x axis, this is my z axis, and this is my y axis again. So these stresses, which are, so basically this stress is sigma xz, that we said it is 0, but it is not 0. And then this sigma xz should balance itself for this differential element that I consider. So for any surface which is parallel to xy plane, then we have this situation. And of course, it varies. Now, the variation is second order, um, parabolic, and then we can actually calculate the force due to sigma x. Sigma x applies here again. And then balance the load, which is sigma x for a differential element, then sigma x dA is my force applies here. This should balance itself with these stresses, which is actually my sigma z. And then from here, from this balance equilibrium, I can calculate tau, we call it tau, which is actually sigma xz, which is V, my shear force at that cross section, divided by I, the moment inertia of the section, multiplied by B here, or any length that I have, multiplied by a quantity. This quantity is called first moment of area. And this is actually equal to AP y bar P. And AP, if I consider the shear stress at this level, then this is the area of, sorry, AP I should say, AP y bar P. So this is AP, and y bar P is, if this is neutral axis, say here, neutral axis, y bar P is the centroid of the area AP with reference to neutral axis. So I refer you to any strength of material book uh, for this. And from here, we recover the shear stress, which is again, from kinematic point of view, it is absent. And then it is required to be present for equilibrium, and from equilibrium, actually, we recover it. That concludes this part 3, I would say, of the video. Part 2 becomes a bit longer, so I made this part shorter. At the end of the series, I will go through an example, which is, or maybe a couple of examples, which is descriptive for all of the theories that I'm going to cover. And to give you some hint here is, besides Euler-Bernoulli, I will cover Timoshenko beam theory, and I will cover the Reddy's beam theory and third order treatment of the displacement, and it recovers fully the shear. So Timoshenko and Reddy will recover the shear from kinematics. We don't need to borrow it from equilibrium, and satisfies the equilibrium equation. And also I will cover two more advanced treatment of beams. One is a kind of a framework, which we call it CUF, C-U-F. I will explain it later. And also a variational approach, which is taking the beam theory basically upside down. Here we go bottom-up approach from displacement to stress and equilibrium. And the variational approach takes it top-down, which is taking care of the strain energy and then minimizes it. And then I will explain that approach, which is called variational asymptotic method. Thank you very much for this. I hope this helps you to understand the beam theory in general, and starting with Euler-Bernoulli, which is heavily used in practice, and sometimes it is not referred to it as a name, but when we say calculate the beam, we use this theory for calculation, mainly using the moment curvature, and for shear, the explanation that we had at the end. And therefore, we can calculate uh, the deflection. And another point to complete here, I didn't write it down, that you can actually get to the equilibrium equation. So if you differentiate the moment curvature two times, if you differentiate it one time, you get to the shear force, and then if you differentiate it two times, then you get to the applied force on the beam, and therefore this becomes a fourth order ordinary differential equation that you can solve. So this is a complete theory, but we have to be aware of the assumptions and limitations, because it ignores the shear or deformation due to shear, or the shear strain and the shear stress. Basically, Euler beam theory, we can say that underestimates the deflection, because it assumes the beam more rigid than it is. And the assumption is valid when our length is much larger than a cross-sectional say dimension. So we have usually a length of maybe 6, 7 meters or order of meters, and the cross section is order of millimeters or centimeters. So we have a very large, as long as this ratio, which is the length over typical cross-section ratio, is above 20 or 20, we are safe to assume the assumptions that we are make. If it is less than that, then your beam, if you use Euler beam theory, increases the error in deflection and sometimes can go to up to 50% error. Um, if you consider Euler beam theory for all the cases, because it ignores the deformation or deflection due to shear stress, as we showed here. Thank you.